Hello everyone, welcome back. In this video, we'll be discussing about the second and the fourth problem of today's weekly contest. Find beautiful indices in the given array 1 and find beautiful indices in the given array 2. Both the problems are exactly similar. The only difference lies in the constraint. And you can solve the second problem using the brute force solution itself, whereas the fourth problem requires some optimization to the brute force solution. And the part where it requires optimization is exactly what we discussed 2 weeks back. If you have been following this channel for a while, I'm sure you are able to approach the fourth problem as well. But anyways, we will be discussing everything from scratch. So let's get started. The problem states that you are given 0-indexed string s, a, b and an integer k. Now index I is beautiful if the following conditions hold, right? Now we have to return the number of all the beautiful indices in the sorted order from smallest to largest, right? So let's take an example. Let's say the given array, a given string s is abcd, a is a, b is a, k is 4. Now we need to return all the beautiful indices. Now the first criteria is that there should be an index I such that starting at I and ending at I plus a dot length minus 1, we have exactly the string a. Similarly, the second criteria is there should be an index j such that starting at j and ending at j plus b dot length minus 1, there is a string b. So basically, starting from I there should be a, starting from j there should be a b, and j modulus I, j minus my modulus should be less than equals to k. So if you look at it, we have a here because a is a, b is also a, so we have a here and b here as well. So I is 0, j is 0, and if you do I minus j modulus, that will also be 0. So 0 is less than equals to 4, so hence first index is a beautiful index. Now this index, for this index to be beautiful, there should be a entire string a that is starting from this index, but that's not the case. So this index is not beautiful. Similarly, these two indexes are also not beautiful, and hence the answer is just 0. Basically only the 0th index is beautiful. So let's take one more example. This is a string, a is my, b is squirrel and k is 15. So now if you look at, is this index beautiful? The answer is no, because for this to be beautiful, we should have an entire string a starting at this index, but a is starting at m, so this can't be beautiful. Similarly, any of these can't be beautiful. The first thing that can be beautiful is this, because starting at this index we have exact a here. Now this is the first criteria, right? But we have to satisfy other criteria as well. So if you look at it, we have squirrel as well before, right? And the index of this particular character here is 4, and the index of this particular character here is 16. So if you do 4 minus 16 modulus, that will be coming as 12, and 12 is less than equals to 15, and hence this index is a beautiful index. So first index that is beautiful is 16. Similarly, any of these can't be beautiful, right? Because they are not m. So for this to be beautiful, there should be exact a here, but there is no a here. So this can be beautiful, and this is indeed beautiful. You can see that there is a squirrel before it, and the difference between the indexes is less than equals to 15, right? So hope the problem is clear. Now what is the brute force solution? So if you have not at least tried the brute force solution, I would strongly encourage you to at least thought about the brute force solution by yourself. So we have these strings. Let's say this is a, right, and this is b, and this is our given string s, and we have k equals to 3, right? Now first thing, we have to match A here, right? So we have to take A. So let's just take A. We have to see, for 0th index to be beautiful, we have to first see whether A is matching. So yes, A is matching. So this index can be beautiful. So let's just mark this index as okay, A is matching here, right? Now this, is this beautiful? The answer is no. This can't be beautiful. Is this beautiful? So there is a matching, right? So we may have index 2 as a beautiful index as well. We don't know. We have to work on other criteria as well, but for now the first criteria is satisfied at least, right? So is this beautiful? No, no. And if you see, there is no other string which is matching. So only indexes which can be beautiful are 0 and 2, right? Now what is the second criteria? Second criteria is there should be a B as well, right? So let's just take B and see where all B exist. So is this matching to B? No, 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 yes. So the first index where B is matching is 4. Now similarly, if you take this one, this is again matching, and similarly this will be the last matching B index, right? So we have 3 indexes which are matching with B, right? Now what is the criteria? The criteria is that for 0 to be beautiful, there should be a matching within the range of k, right? So either plus k or minus k, because there is modulus, right? So either so there should be a matching index B between -3 and +3, right? So is this is B exist in any of these indexes? The answer is no, because B doesn't exist in between +3 and -3. 0 is not a beautiful index. Now what about 2? So is 2 beautiful? Again, for 2 to be beautiful, there should be a matching B in between 2 minus k and 2 plus k. So 2 minus k is -1 and 2 plus k is 5. So this time the answer is yes, because there is a matching character or matching starting character 4 which lies between -1 and 5. So hence 2 is a beautiful index. So the answer to this entire problem will be array which only contain 2, because 2 is the only one which is a beautiful index, right? So this is exactly what brute force solution would look like. Now what will be the time complexity of this entire solution? So we are doing 3 things. Notice we are first matching whether A exists or not, right? So if you remember, we have done okay, it is matching, it is matching, it is matching, and so on and so forth, right? So for each index, what we are doing, for each indexes we are iterating over the length of A, right, to figure out which all string are possible matchings of A and are possible beautiful characters, right? So with this much complexity you will get this first array, right? Similarly, you are also matching for B as well, right? So again, same thing, for each index you are iterating over the entire length of B. So there are n indexes and you are iterating over the entire length of B. So this is the complexity of figuring out the second array, right? Now you have both first array and second array with you. Now you need to find out what is the which of these indexes are actually beautiful, and how you will figure out. For each index you have to, let's say, iterate over all of these and figure out if this lies between the ranges, right? So that is one way, and second way could be you just iterate over -k and +k, and there are other ways as well, like you can do a binary search as well and figure out this. So this third part is exactly not the bigger problem, because for each index you can do a binary search and figure out, okay, I want everything between +3 and -3. So I will do binary search for -3, I will get this index. I will do binary search for +3, I will again get this index. So because R and L are both same, it means there is no index in between, right? Similarly, for 2 you will do binary search, you will get, for -1 you will get this index, and for 5 you will get this index. So there is difference of 1 between R and L, so it means there is one index which is in between -1 and 5. So that's how you can figure out the third part and optimize it if required. So if you do brute force, like for each index, trying out each index, that will take you order n square. But as mentioned, you can simply make it n log n by doing a binary search as well, right? So the third part is not that big. So overall the complexity is n into LA plus LB plus log n, right? So that is the overall complexity of this entire brute force algorithm. Now this complexity is sufficient to pass the second problem. So if you look at the second problem, which is given array 1, you have n is 10 to the power 5, b is 10, length of both a and b is 10, and k is also 10 to the power 5. So n is 10 to the power 5, these two are 10, and this log n will also again be somewhere 20, because log of 10 to the power 5 will be less than 20. So overall this is 10 power 5 multiplied by 20 or 40, so which is within the time limits. So if this problem was completely new to you, I am very sure you should, if you code this entire thing by yourself, you will be able to understand this kind of problem by yourself. But if you have already solved this brute force solution, then you can move forward. So now this constraint is not sufficient for solving the fourth problem, where a and b are also of same length, and this time s is also of larger length. So we have to optimize this. Now which of these parts do we need to optimize? We need to optimize, this is okay, right? Log of 10 to the power 5, which is okay. We have to optimize on these two parts. Now what these two parts were doing, they were with n into LA, you are trying to figure out the first array. In other words, which all indexes in A are matching with B, matching with the string A. Similarly with n into LB, you were trying to figure out which of the indexes of S is matching with B, and you will get this array, right? So these are the two things you are figuring out with n into LA and n into LB, and you have to optimize on that. So you have to get these two array efficiently, right? So how to get these two array efficiently, we'll discuss about it, but let's just quickly look at the pseudo code just to make things a bit more clear. So we have figured out first A indexes, we have figured out B indexes, and after we have done these two things, we will, for each A index, I will see if there is anything in between this range in B index or not. If there is, then current A index is a part of my result, otherwise no, right? So these two part is something we need to now make faster. This part is already efficient. We know that this particular if condition can be answered using binary search in just log n time, right? So how to optimize on these two parts? So what is the problem? Problem is, given a string, you need to figure out which all places this A occurs. Now there are various possible solutions. One, you can, if you already know about string matching algorithms like Z algorithm, you can easily figure this out. You in just order n plus LA time. Instead of n into LA, you can figure out in n plus LA time. That will be sufficient for the given time constraint. But if you don't know about it, you can simply do hashing. Hashing we have discussed in previous videos as well, but just for clarity we will discuss it one more time here in a very brief manner. So the problem is we have given this string s and we have to figure out which of these indexes is equivalent to this string. So what we will do, we have, if we keep on matching character by character, we have seen we will take, it will take order n into LA time, right? Now we can't afford this LA here, right? We have to somehow make it order n into 1 or some constant factor, right? Which in turn implies that you can't go character by character. So one of the ways, just hash this entire thing and get an integer out of it, right? So we hash this entire thing. How to hash is a different question. We hash this entire thing and get an integer out of it. Now for any index here, let's say for the index 2, we know what is the last index that we care about because length is 3, so this should also be 3. Now we will figure out the hash of this part. Let's say it is h dash. So if h dash is equals to h, then we will say okay, this particular thing is matching with this. If it is not, then we'll say the current index L is not a valid match for the given string, right? So that's basically the entire approach. Now the only question remains is how to figure out this h or h dash for that matter, right? So for finding out h, you can have different ways. So it's just a mathematical representation for this given string, right? So you can have any mathematical expression that can convert the string into a integer. So an expression could be summation of all the characters. So you can say okay, a is 1, b is 2, b is 2, a is 1, b is 2, a is 1, and so on and so forth. Now if I tell you okay, find me the hash of this entire string, you can simply sum this entire thing and you will get some number that you will say is the hash of this complete string. So this is one possible way, but in this case there will be more collisions. How? Let's say you have this particular string ABB. Now you are hashing it. So what will be the hash? Hash will be 1 plus 2 plus 2, right, which is 5. Now let's say there is another string BAB. Now what will be the hash of the string? 2 plus 1 plus 2, again 5. So both this hash are equal, but the strings are not equal, right? It means there is a collision, or the probability of collision is more in this hash function, which makes sense as well because you haven't considered anything with related to indexes in your mathematical expression. So the information that A is present at index 1, B is present at index 2 is kind of lost here, right? And that's why you can see BAB is also giving a match with this, right? So next thing you can do, okay, I need to take care of indexes as well, so let me add a index factor here. So now this particular, the hash, the value for the first index would be the value of the character, which is 1, plus the index 2. So 1 plus 1, 2. Value of the character is 2 plus the index, so 2 plus 2, 4, and so on and so forth. Now to give the hash of this entire string, you can simply sum this entire thing and you will have the hash. But again, this will have lot of collision. You can simply try out with exact same examples and you will see it is still colliding. And the reason for collision could be you did take care of the indexes, right? But because this is sum, so, and these indexes and characters are kind of closely placed. So there is a character A, there is an index 1, so A plus 1 will be 2, right? And now let's say there is a character, so let's say there is a character A at index 5, let's say, so 5 plus 1 will be 6. Now there are various possible scenario because B is there, so you can simply put b at index, let's say 2 plus 4, so at index 4 you will also get 6. So because you can easily find out the corresponding counter cases, breaking this particular hash function is easy, right? Now why you are able to find out this cases easier, because this was just summation, and because it is summation, with just a few operation of subtraction you can figure out what will be the counter cases. So one of the better hash function is when you do multiplication, you can say ch multiplied by p power I, not I. Even if you do I, you can see you can figure out the counter cases easily. So we have now chosen a prime p, we have raised the index to that power and then multiplied by the current character. Now here if I told you, okay, a is present at first index, so the value of this would be a into p. Now give me the counter case, you will struggle. You have to figure out, you have to do a lot of computation to actually make it collide, and that's what a good hash function should be. So we can have this kind of hash function. Basically a is p, b is 2 p power 2, then this particular b is 2 p power 3, and so on and so forth. So if the hash of this entire string would simply be this summation of this entire thing, and you will get the hash. So now that we know the hash function, so let's just get rid of these entire things for time being. So now we know how to figure out the hash of a particular string. So we can simply figure out the hash of this entire string in just order layer time, right? We can simply keep these things pre-calculated, p power 1, p power 2, p power 3, all these things can be pre-calculated, and we can simply iterate over the string and do summation in this fashion, and we'll get the hash in just order L into A time. Now finding out the hash of this L2R, if you do it naively, what will you do? Okay, I need to find out the hash of BBA. Again I will do 1 into p power 1, 2 into p power 2, sorry, 2 into p power 1, 2 into p power 2, and 1 into p power 3, and then I will sum this all up and I will get h dash. If you do it in this fashion, there is no advantage, because you are again iterating over the length of A for each indexes, which is as bad as the previous n into LA solution, right? So you have to somehow figure out the hash of a substring faster, and because it is summation, the obvious choice is prefix sum. You can maintain a prefix sum. You can say, okay, I will maintain a prefix sum of this entire array, where a particular index will denote what is the sum of everything from 1 to 6, right? Now if you want the value or the hash of everything between, let's say, 4 and 6, what you will do, you already know the sum of everything between 1 and 6, let's say it is x. You already know sum of everything between 1 and 3, let's say it is s3. So this is sum of everything between 4 and 6. But there is a catch here. The catch is, if you figure out the sum of everything between 4 and 6, what you will get p power 4 plus 2p power 5 plus p power 6. But if you isolate this entire thing, ABA, and then figure out the hash, then the hash would be p power 1 into 1, 2p power 2, and then plus p power 3. So this is the final hash you will get, but what you are getting is p power 4 to p power 5 to p power 6. So you can simply divide this entire thing by whatever you are getting here. You can simply divide this entire thing by p power 3, and you will get this exact same thing from this particular summation. Because why you are not getting this? Because here the starting point is 4, but you want everything to start with 1. So everything has p power 3 as extra, p power 4, p power 5, p power 6. So you just divide it by p power 3 and you will get the answer. Now division can be hard, because you will also keep on taking modulus so that things don't go beyond 64-bit integer. So instead of division, what you can do, you can multiply this h by p power 3 and then compare. That is a standard way, right? So that way you are now able to figure out the hash of a substring in just order one time. You initially figure out this particular prefix array in order n time, and after that you can figure out the hash of this entire substring in just order one time. And for each hash you can simply compare it with the hash of this string, that will also take order one time. So for each index, to know whether it is matching with this entire string or not, you are now taking just order n time, right? So hope this entire solution makes sense. If you still have doubt, I would encourage you to watch the last 5 to 10 minutes of the video and understand that as well. So if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself. And if you are able to code this, I will also link the problems of the previous week's weekly contest, which can be solved in very similar fashion. You can watch and solve that as well. So next we'll be looking at the code. The code is exactly what we discussed. So this hashing technique is also known as Rabin-Karp. You can search about Rabin-Karp algorithm online and you will get the exact same thing, right? So we have to figure out the beautiful indexes. We first figured out A indexes, B indexes using Rabin-Karp, and after that we simply iterated over all the A indexes. So these are not required. I think I'm not sure why I use this, but we simply iterated over all the A indexes, and after that we figured out where is A index minus k starting in B indexes array, and where is A index plus k starting in B indexes array. If there are elements in between, it means we have at least one match and we will use A index, otherwise A index is not a beautiful index, right? Now finally this Rabin-Karp, this here S denotes the pattern, which in our case is this string, small string, and T denotes the text where we need to match this pattern, right? So we figured out the sizes, that is fine. Now as you remember, we have to somehow find the value of p power 2, p power 3, and so on and so forth, and use it with while calculating the prefix sum. So we calculated those beforehand using this simple algorithm. So if the value p power 1 is equals to p, now p power 2 will simply be whatever the value here is multiplied by p. Similarly, p power 3 would simply be whatever the value here multiplied by p, right? So that's what we have done. Whatever the value at previous index multiplied by p is the current p power. Now once we have that, we simply figure out the hash of the given text. So if you remember, we also have to keep the prefix sum. So h of I plus 1 is simply h of I plus this entire thing. This is the character and this is the p power, right? Now once we have the hash and the prefix sum, we also figure out the hash of the given string s, right? This is this h in our explanation. Now we have to just figure out h dash for every index and it will match h and h dash. So for every index we are figuring out the hash of the string starting at index I and ending at I plus s minus 1, right? So the hash of this entire thing is current h. We have to check if current h is equals to hs multiplied by p power I modulus mod. Why p power I multiplication? Because if you remember, this will be p power 1, p power 2, p power 3, but when you figure out the prefix sum, it will be something larger based on which indexes you are currently referring to. So whatever index you are at, you will simply divide this entire thing by p power 1 less index. So if you are at index 4, you will divide the entire thing by p power 3. So instead of dividing, we will multiply, so that we don't need to worry about the division operators in terms of modulus. So that's where we simply multiply the hash of the string with p power I and take the modulus, and if it matches, we know that there is a match, right? Now this is what the entire solution is. This will pass the given time constraint and will not have any collision. But if you submit the same thing in code forces and other things, this may or may not pass, and you have to make your hash function a bit you have to strengthen your hash function a bit further. And for that, one of the usual trick is, instead of maintaining one hash hs, you also maintain hs2, where you take different modulus or you take different prime. So you compute this and you do this entire exercise with two different hash functions, and if both of them give the positive result, you then consider a match, otherwise you will not consider a match. So that will further reduce the probability of collision. So that those are the simple tricks, but in these kind of problems you can also apply JIT algorithm, which is not a probabilistic algorithm but rather a simple string matching algorithm, which also fits in the given time constraint, or which also can find this entire thing in just order order t plus s size, right? So hope this entire solution makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.